Hello everyone, welcome to another lecture of the course Digital Signal Processing. Till the previous lectures, we have seen the concept of discrete Fourier transform, inverse discrete Fourier transform. We have also seen various properties of DFT and IDFT. We know that the analysis equation is given by this formula, and similarly the synthesis equation is given by this formula. Now in this lecture, let us try to represent these two equations, that is analysis and synthesis equation, in matrix form. So before that, what we will do is we will just consider this term here, that is e to the power minus j 2 pi by n, and we will represent it as Wn, and this Wn is known as the Twiddle factor, and it is basically the nth root of unity. Now we know that this e to the power minus j 2 pi is basically equal to 1, and now if we take its nth 1 by nth power, that is nth root, so we would be getting e to the power minus j 2 pi by n, which would be equal to 1 to the power 1 by n, and therefore this factor e to the power minus j 2 pi by n is basically the nth root of unity. So this Twiddle factor given by Wn, which is given by this formula, is nth root of unity, and using this Wn we can make changes in these two formula. So we can write this x of k as summation n running from 0 to n minus 1 x of n into, so this factor, that is e to the power minus j 2 pi by n, can be simply represented as Wn, and it is raised to the power of kn. So this is the new representation for this analysis equation. Similarly, this x of n can be written as 1 by n summation k running from 0 to n minus 1 x of k. Now this e to the power j 2 pi by n can be written as Wn to the power minus 1, and now it is raised to the power kn, so it can be written as 1 by n summation k running from 0 to n minus 1 x of k Wn to the power minus kn. So this is the synthesis equation, and this is the analysis equation written using this Twiddle factor. So now we will consider these two equations and try to represent it using matrix form. So initially let us consider this analysis equation. So we have it as x of k equal to this formula, and we know that the range of this k is from 0 to n minus 1. So for this x of k, we are going to get n points for k ranging from 0 to n minus 1. Similarly, we are going to vary this n from 0 to n minus 1. And the points from 0 to n minus 1 can be just found by substituting the corresponding value of k in this equation. So if we need to find the value of x of 0, then we need to just substitute this k as 0 in this equation, and when we expand it, it is given as x of 0 Wn to the power kn, so it is 0 into 0, the value of n here, plus x of 1 Wn to the power 0 into 1, so it is kn again, plus and so on x of n minus 1 Wn to the power 0 into n minus 1. Similarly, this x of 1 can be represented by substituting k equal to 1 in this expression. So we get it as summation n running from 0 to n minus 1 x of n Wn to the power k, which is equal to 1 into n, and again if we expand it, then we get something like this, and so on. We can repeat this process till we have the value of k as n minus 1. So we have it as summation n running from 0 to n minus 1 x of n Wn to the power n minus 1, which is the value of k into n, and again if we expand it, then we get the expression something like this. So we have the representation something like this. Now if we observe this part here, that is x of 0, x of 1 and so on till x of n minus 1. So this can be represented in a vector form something like this. So we can write it as x of 0, x of 1 and so on till x of n minus 1. So we can consider it as a vector. Similarly, if we observe the value of this x here, that is x of 0, x of 1 and so on till x of n minus 1, it can also be represented in a vector form something like this. That is, we have x of 0, x of 1 and so on till x of n minus 1. And now we need to obtain this left hand side using this right hand side. Now if we observe these equations, what we can see is if we need to get matrix multiplication from these equation, so we need to have a matrix here something like this. So we need to have a matrix multiplication, and if we observe for x of 0, this x of 0, that is small x of 0, is to be multiplied by Wn to the power 0 into 0. So in order to get capital X of 0, we need to multiply small x of 0 by Wn to the power 0 into 0. Similarly, in order to get plus, we need to have this x of 1 multiplied by Wn to the power 0. So here we need to have it as Wn to the power 0 into 1 and so on. We have it as Wn to the power 0 into n minus 1. So if we consider the matrix multiplication, so it would be row into column. So it would be Wn to the power 0 0 into x of 0 plus Wn to the power 0 1 into x of 1 and so on. Then Wn to the power 0 into n minus 1. So this factor here multiplied by x of n minus 1, and that would be corresponding to the value of x of 0. Similarly, if we need to find the value of this x of 1, then here we would be having x of Wn to the power 1 into 0 multiplied by this x of 0. Then we would be having Wn to the power 1 into 1 and so on till Wn to the power 1 into n minus 1 and so on. If we continue and try finding the value of x of n minus 1, then we would be getting Wn to the power n minus 1 into 0, Wn to the power n minus 1 into 1 and so on till Wn to the power n minus 1 into n minus 1. So this x of 0 can be calculated by multiplication of the first row into this column. Then x of 1 can be obtained by multiplication like this, and this x of n minus 1 can be obtained by multiplication like this. So this vector, that is x vector for x of k, can be obtained by multiplying this matrix with the vector for x of n. So now what we can do is we can just represent this vector by x, represent this matrix by say Wn, and represent this vector here by small x. So this is the matrix representation. This is the matrix representation for the analysis equation of DFT. Now if we observe carefully, this vector here, that is x, is n cross 1 dimension. This vector again here, that is for x of n, is n cross 1 dimension, and this vector that we obtain here, the matrix that we have here is of the dimension of n cross n. Now each row corresponds to a particular value of k. So the first row corresponds to k equal to 0, the second row corresponds to k equal to 1, and so on, and the last row corresponds to k equal to n minus 1. Similarly, each column corresponds to a particular value of n. For example, the first column corresponds to n equal to 0, the second column corresponds to n equal to 1, and so on. The last column corresponds to n equal to capital N minus 1. So this is the matrix, that is Wn, which is n cross n dimensional. So we have the matrix representation for this analysis equation as this vector x, which is given as Wn, which is n cross n matrix, multiplied by this vector x. So now let us go ahead and try to find the matrix representation for the synthesis equation, and we know that the synthesis equation is given something like this. So we have it as 1 by n summation k running from 0 to n minus 1 x of k Wn to the power minus k, and again when we need to find the value of this x of n, where this n again ranges from 0 to n minus 1, then we need to just substitute the value of n as 0, 1 till n minus 1 and substitute in this expression here and simply expand like this. So we know that if we have x of 0, then we need to substitute the n as 0, and then we have it as summation k running from 0 to n minus 1 x of k Wn to the power minus k into 0 and scaled by the factor of 1 by n, and it can be expanded something like this. Similarly, when we need to find the value of x of 1, then we just need to substitute the value of n as 1 in this expression and simply expand, and same goes with when we need to find the value of x of n when n equal to n minus 1. So these are the expanded versions for the value of x of n for different values of n ranging from 0 to n minus 1. Now again, this part here can be represented as a small vector of n cross 1 dimension. So it can be given as x of 0, x of 1, and so on till x of n minus 1. So we have this n cross 1 vector, and again now we have this scaling factor here, and we would be getting again a matrix. And now again we would be having a vector corresponding to this x of 0, x of 1, and so on till x of n minus 1. So we have here x of 0, x of 1, and so on till x of n minus 1. Now in order to get x of 0, the Twiddle factors that we have are like this. So these are to be arranged in the first row. So we have Wn to the power minus 0 into 0, then Wn to the power minus 1 into 0, and so on to Wn to the power minus of n minus 1 into 0. So it is Wn to the power minus of n minus 1 into 0. So this matrix is like this. Similarly, when we need to find x of 1, then the Twiddle factors that we have are like this. So we have Wn to the power minus 0 into 1, then Wn to the power minus 1 into 1, and so on till Wn to the power minus of n minus 1 into 1, And similarly, when we need to find the value of x of n minus 1, then at that time the Twiddle factors are given like this, which can be again arranged in this last row. So it is given as Wn to the power minus 0 into n minus 1, then Wn to the power minus 1 into n minus 1, and so on till Wn to the power minus n minus 1 into n minus 1. Now we know that this vector is given by x. So this vector here is x. So it can be written as 1 by n multiplied by some matrix multiplied by this vector is known as capital X. So now let us try to find what exactly this matrix is. If we observe this matrix here and compare it with this matrix that we had obtained earlier, so we can see that the matrix that we have obtained here is simply transpose but with a negative sign in the exponent. So if we compare these two matrices, so if we take the transpose of this matrix, then this entire thing would be coming as rows, means simply the column and rows would get interchanged. Moreover, if we have a negative sign at the exponent, then we are going to get the same matrix, which means that this matrix here is simply the Hermitian of this matrix. So we can represent this as Wn Hermitian, and this is the matrix form representation for the analysis equation, for the synthesis equation for the n-point DFT. So in this lecture we saw that we can represent the synthesis and analysis equation for DFT in the matrix form, and we know that the analysis equation can be represented as x equal to this x Wn, and the synthesis equation can be represented as x equal to 1 by n capital X Wn Hermitian. So this is basically, this capital X can be represented as Wn into small x, whereas this x can be represented as 1 by n, then Wn Hermitian multiplied by capital X. So this is the matrix representation for the synthesis and analysis equation, and we know that this vector x is given as x of 0, x of 1 and so on till x of n minus 1. Similarly, this vector capital X is the vector for x of k, and it is given as x of 0, x of 1 and so on till x of n minus 1, whereas this matrix Wn is given like this. So in this lecture we saw the matrix representation for the synthesis and analysis equation of DFT. So let's stop here. Thank you.